afternoon. I am Riya Soni and I am going to present on ASIC implementation of AI Edge networking chip at 28 nanometer technology node and its various timing optimization techniques at each stage. This presentation is prepared by Riya Soni from Department of Electronics and Communication, Dharamsala Desai University, Shani Patel, Physical Design Engineer in eInfochips, Ahmedabad, India, and Nilesh Ranpura, the Director Engineer of eInfochips, Ahmedabad, India. Agenda for the day is introduction, followed by network on chip architecture, physical design flow, and implementation of network on chip at 28 nanometer technology. People nowadays are habituated by instant communication. At the same time, mobility is also demanded. Communication from anywhere and anytime requires good network on chip installed in the device. Network on chip requires huge on chip communication and over a fraction of time. Traditional network on chip architecture interconnects all the routers via buses. This topology was good approach with single processor. Nowadays, multiple processors chip on chip is most preferred. This type of network on chip operates on very high frequency. ASIC design for such a high speed chip becomes challenging in terms of timing closure. Timing closure is one of the ASIC important essential part of ASIC design flow. Hence, it is needed to be taken care of at each stage of the physical design. Hence, in this paper, physical design of such a networking chip is discussed with various optimization techniques such as used at each stage. It is intended to reduce worse negatives like with increase in number of transistors in small area, the cell density increases. Current network on chip architecture cannot respond to such millions of transistors on a chip. They are not capable to cope up with the increasing requirements of the future SoCs in terms of performance, timing, and performance, power, and timing. On-chip buses can serve a limited number of routers, and beyond that, performance degrades due to the bus parasitic capacitance. This may lead to delays. Therefore, networking on-chip ASIC design is challenging nowadays. To overcome this, mesh network is much preferred. So, basic network on chip architecture. So, as you all know, topology means how nodes are connected to each other. Topology of a node impacts on very much on latency and bandwidth. So, traditional bus-based architecture is being replaced by mesh topology. Here, every routers are directly connected to each other. So, no centralization is available in mesh topology. Hence, packets can easily and quickly travel, and there are only small space to travel. There is nothing more to travel for these packets. So beyond this, NOC must support a wide bandwidth and quality of service. Because of the timing closure are challenging. Because of this, timing closures are challenging in network on chip. In mesh-based topology, the interconnection of the resources and the switches are independent of size of the network, which is a drawback of the traditional bus-based architecture. In bus-based architecture, with increasing size of the network, the net length increases, so it results into more parasitic capacitance, and which includes inserts delay in the network. So this is what is the reason why we get high delays while designing ASIC for network on chip. So here, as shown in the figure, all the routers are connected in the Manhattan-like structure as shown in the here. A brief about physical design flow is shown. Here, RTL, SDC, technology libraries, all the timing libraries, all the link libraries, all the TLU plus file, UPF file is given to the input of the synthesis stage. Here, synthesis is just a prerequisite step for physical design flow. At the end of synthesis, we get a technology dependent netlist in a Verilog or VHDL, whatever the language it might be, and we obtain a netlist which is technology dependent. This netlist serves as an input to floor plan stage. At floor plan, we actually decide the dimension of the chip, and we just try to place the macros inside the core area. In power planning, a power mesh is created to give VDD and VSS to all the standard cells. In placement stage, all the standard cells are placed inside the core. At the CDS stage, we try to get a balanced tree and give clock pulse to all the sequential cells. And at the end, when everything is done, we do the physical routing at routing stage we try to route all the signal as well as clock signals at this stage. So we'll talk about in this work physical designing of ARP block 5 is carried out. Chip designing briefly glances upon the three aspects: performance, power and area. To achieve this, various techniques are applied during the entire physical flow. Here timing violations were taken into consideration and we try to reduce this at each stage. Some of the specifications of block 5 is given in the following table. Its operating voltage is 0.81 volt. Its operating frequency is 0.78 gigahertz. Its pole width and height are 1167 cross 972 micrometer. There are 6 macros in this block and total IO ports are 982. Various techniques used to reduce timing violation at different stages of physical design. So there are various optimizations performed during each stage of physical design. They are listed in the following table. DFA stands for data flow analysis. So here we try to see virtual connections between two macros and we place the macros which are talking to each other nearby as per the DFA analysis, and we try to see which macros are talking to which port and which pins so as we can put it nearby to that particular port. We used magnet placement at before placement and after flow planning stage. Here we try to fix an object, most probably a macro, and all the cells talking to that macro are placed nearby that macro so as we can try to reduce the net length, so as delays can be reduced. Buffer insertion in the path can reduce the transition time and net length at the same time. So we try to insert buffers where WNS is very high. Then gate cloning. Gate cloning is duplicating a particular high fan out net. Pin swapping is used when it swaps the nets of the input pins to reduce slack. Flow planning of networking chip. In networking chip, the core width is 1167 micrometer and its height is 970 micrometer. Its aspect ratio is said to be 0.83. We had 6 macros in the design and they are placed as shown in the figure. As the flow plan is for one particular block and not the entire network and chip, so we had provided a blockage in between. At this stage, we had inserted tap-well cells and to avoid latch up and end cap cells to add protection to the standard cell while manufacturing. In power planning, we provide a mesh type of structure to all the standard cells. For power planning, M9 layer is used for VDD and M5 is used for VSS. At placement stage, as we have seen, the macro above the blockage was chosen as a magnet and all the standard cells were placed nearby that particular macros. Then buffers were inserted near IO ports. PS1 OPD is used to refine the critical path to improve WNS for setup improvement. At this stage, without optimization, the WNS was 360 picoseconds, which was after reduced to 160 picoseconds after applying the standard of optimization. At this stage, spare cells and filler cells were added. In this stage, clock tree synthesis of networking chip. Here there are 7 clocks in the design. The master clock's time period is 0.13 picoseconds, so its operating frequency becomes 0.75. Rest all the 6 clocks are generated clocks. All the clocks have 50% duty cycle. At CDS stage, the WNS was 100 picoseconds. After applying optimizations, before applying optimization was 310 picoseconds. After CDS stage, routing was done. Here, congestion-driven routing is taken into consideration because of which there was no congestion in the design. After this, The WNS at the stage was 120 picosecond, which was before optimization applied, it was 320 picosecond.